Depth of BST given insertion order. So this is a premium medium problem. We all know what is a BST, right? The left subtree of any node will always have values lesser than the current node, and the right subtree will have values greater than the current node. Also, the left and right subtree both should be binary search tree. And what is the depth of a binary search tree or any tree? It's basically the number of nodes in the longest path of that tree. So binary search tree will not always be balanced because it depends on the insertion order. So if you are inserting elements in the increasing order or decreasing order, so always the depth will be order of n. But in other cases, it can be dependent on the insertion order. So given an insertion order, we have to find out the depth of the binary search tree. Now consider a few examples they have given here. First example is 2, 1, 4, 3. So first you are inserting 2, then 1 that is in the left side of 2, then 4 it's coming in the right side of 2, then 3. So it will go in the right side of 2, then left side of 4. So the depth here is in this longest path, that is no number of nodes in this longest path is 3. So next we have this one 2, 1, 3, 4. 2, then 2, 1, then 2, 1, 3, then 2, 1, 3 and 4 here. So here also depth is 3. Consider this one 1, 2, 3, 4. So yeah, this is basically we are inserting in the increasing order. 1, then 1, 2, then 1, 2, 3, then 1, 2, 3, 4. You see the length, the depth here is the number of nodes basically, that is order of n. So in all these examples we have only 4 nodes 1, 2, 3, 4, but the orders are different and that's why the depths are becoming different. So the brute force approach to solve this problem is by actually creating the binary search tree. So for this problem, for this order, we can first create the node 1, then 2, then 3, then 4, right? So what will be the time complexity for each node insertion? So for 4, we have to check with first 1, then 2, then 3, then we can insert 4, right? So in the worst case, it will be order of n for each node insertion. For n nodes, it will be order of n square. Now see a few constraints here. So if n is the order of length and or we can say n is the number of nodes, then n is max value of n is 10 power 5. So n squared it will go till 10 power 10, right? So it will give time limit exception. So till 10 power 8 it runs within a second, right? And if it goes after above 10 power 8 means 10 power 9 means 10 seconds, so it will give time limit exception. So we have to come up with a solution that is at least n log n or see if we can do better. So here we'll see a few random examples of binary search tree. So let's consider binary search tree of just 3 values 3, 4 and 5. I'm not considering the actual problem here where the node starts from 1 to n, but it's just random examples just to have some intuition. So if there are 3 nodes, then it can have 6 permutations, right? So 3, 4, 5, 3, 5, 4, 4, 3, 5, 4, 5, 3, 5, 3, 4 and 5, 4, 3, right? And respective binary search trees are given here. Also in green, I have the depth of each node. So first thing we can notice is each node has depth that is 1 plus its parent's depth. Also there are few binary search tree that are balanced, this one and this one. The rest here, these are not balanced, right? So the maximum depth are 3 here, that because of that. Here I have written the depth of each node, but we want to know the depth of the whole binary search tree. So that will be what? That will be the max of this all depth, right? So also one more thing to notice here, for each of these binary search trees, the in-order traversal order is always sorted order. That is 3, 4 and 5. You see 3, 4, 5. That's one thing we have to keep in mind. Next, we see the problem in our brute force approach. Consider this is the insertion order 5, 4, 3, 2, and this is the way we are creating the tree. So first 5, then we are inserting 4, then 3 and 2. What is the problem for our brute force approach, right? So for each insertion, in the worst case, it will be order of n. So how do we improve this? Can we get a different data structure where insertion will be not order of n, less than order of n, right? So we can use something like Python sorted set. Also, if you are using Java, we can have a tree map based approach, but here I am discussing the Python sorted based approach. Why we are doing this? Sorted set is sorted list or sorted set. Sorted list I will be using here. So sorted list will keep the nodes values, right, in the in order traversal order. That is a sorted order, and this sorted list will actually internally use some balanced binary search tree. So the insertion will be order of log n, not order of n here. So let's say we are getting 5. I'll insert 5 here because 5 is the last element, right? Then I'll get 4. I'll insert 4 here. Then I'll get 3. I'll insert 3 here. Then I'll get 2. I'll insert 2 here. So then insertion is not a problem. So earlier we had a problem that insertion was taking order of n. Now insertion is order of log n. But the problem here is this is generic for all combinations of 4 nodes, right? So in order traversal is always same, but I need to get the depth of each node. And how do we get the depth of each node? That will be 1 plus its parent's depth. Now how do I decide which one is the parent of each node when I am inserting? So for that, let's see few other examples here. Let's say 3, 4, 5. I am inserting 3, then I am inserting 4. So 4 is the right child of its parent, right? So 4 is greater than 3, so 4 will be right child, and its depth will be 2 because parent's depth is 1. Consider this one. Here I am inserting 5 first and then 4. 4 is left child of its parent. So parent is depth of parent is 1. Depth of this current 4 will be 1 plus 1, 2. So for each node, it can be either a left child of its parent or the right child of its parent. And that how we'll decide in the insertion order. If we just check any node, let's say for 3, right? We don't have the 2 at present, right? We inserted 5, we inserted 4, then we inserted 3. So we don't have this 2 at present, right? So we just have here 4, 5 and this is the 3. So what will be this parent? Parent will be 4. We'll see a few other examples that will clear the problem here, clear the doubts here. So and also see the depth how we are calculating 5. The depth of 5 will be 1 is the first one, right? Depth of 4 will be 2 because 4 is child of 5. Depth of 3 will be 3. Depth of 2 will be 4 because this is we are inserting in decreasing order, right? So the depths are increasing in this way. Now let's see one different example. The insertion order is 4, 5, 2, 3, right? The tree is this one. 4, then we insert 5, then 2, then 3. Now we inserted 4. The depth is 1. Now inserting 5. The depth of 5 will be 1 plus 1, 2. Next inserting 2. Parent of 2 is 4. It has depth 1. So parent of 2 will depth of 2 will be 2. Inserting 3. Depth of 3 will be 2 plus 1, that is 3. Now how we will insert it in this in order slots or in order sorted list that we will be having. So we get 4. Where will be 4 or 4? 4 will be inserted in this position, right? How we are inserting that we will see next, but it's just conceptually see 4 will be here, right? So what is the parent of 4? Do we have anything in the left side of 4 or right side of 4? No, right? So not 4 is not left child or right child of any node. So 4 will be the root. It will have depth 1. Next we are inserting 5. 5 will be where? After 4, right? So we will be inserting 5 after 4. What is parent of 5? So 5, parent of 5 is 4 because 5 is right child of 4. So parent of 5 will be in the left side, right? So depth of 5 will be 1 plus 1, 2. Next we are inserting 2. So 2, where 2 will come? 2 will come at the left side of 4, right? So because 2 is less than 4, so 2 will come here. Forget there is a slot here. So just let's say current at present we are inserting 2 at the left side of 4. What is the parent of 2? That is 4. Because 2 is the left child of its parent here in this lot will be at the right side. So at the right side we have 4. We don't have 3 yet, right? So 3 we have not inserted. So at this insertion order, at this moment, we'll see at the left side or right side. At the right side we have the parent. Its depth is 1. So the depth of 2 will be 2. Next we are inserting 3. So 3 will come here, right, between 2 and 4. And what will be the depth of 3? Its parent is 2, right? Its parent of 3 is 2 and depth of 2 is 2. So parent depth of 3 will be 3. Now here, see how do we get the parent of 3? How did we get? So we are not actually constructing this tree, right? We are just inserting value in this in order slots list, the sorted list. So how do we get the parent of this current node 3? It can be either in the left side or the right side. How do we decide that? So parent of 3, in the left side we have 2, left side of 3 is 2 and right side of 3 is 4. Which one has larger depth? This one. So the larger depth one will be parent because smaller depth one has come before, right? And this larger depth node has come just before this current node, right? So from the left side and right side both will check and we'll just take the maximum depth one node. That will be the parent of the current node. So its depth is 2, the depth of 3 will be 3. Now let's just have written it properly, like parent of any node will be either left of B or right of B while inserting at that moment, but that will have larger depth. Now and also the depth of any node will be 1 plus depth of its parent. Here I am just showing with one example. Consider this is the insertion order. Now we have this sorted list. So here I will be inserting this elements, this ordered elements, right? So this insertion, each insertion will be order of log n. That's the way sorted list works, right? So and one more thing is we need to know at each point the depth of its parent. So to keep track of the depths we need a hash map or dictionary. So I have one dictionary here that will keep track of the depths of each node. So in this sorted list, I'll first insert 3. Now before inserting, I am just adding 2 extra nodes, that is 0 and max, because in this problem we have nodes from 1 to n, right? Now I am inserting 3. What will be the depth of 3? I will check in the left side and right side. 0 and max both have depth 0, so depth of 3 will be 1. So it's basically nothing we have at the left or right, or that this current node 3 is not left or right child of any node. It's basically the root node, so its depth will be 1. Next we are inserting 5. 5 will come after 3, right? So its left is 3, right is max. Depth of 3 is 1, depth of max is 0. So parent is 3. So depth of 5 will be 1 plus 1, 2. Next I am inserting 1. Its left is 0, right is 3. So 0 has depth 0 and 3 has depth 1. So depth of 1 will be 2. 1 plus 1, 2. Next I am inserting 2. Its left is 1, right is 3. 1 has depth 2 and 3 has depth 1. So which one has larger depth? 1. So 1 will be the parent of 2. So depth of 2 will be 2 plus 1, 3. Next 6. 6 will come after 5. So left is 5, right is max. So of course parent will be 5. Depth of 5 is 5. So it has depth 2. So depth of 6 will be 3. Next we have 7. 7 will come after 6. So of course the depth parent of 7 will be 6. So depth of 7 will be 3 plus 1, 4. Now we are inserting 4. So left of 4 is 3 and right of 4 is 5. So 3 has depth 1 and 5 has depth 2. So that means 5 has larger depth. So 5 is the parent of 4. So depth of 4 will be 2 plus 1, 3. So the overall time complexity we already talked. Because of the sorted list, balanced binary search insertion, the it will be order of log n for each insertion, and overall it will be order of n log n. As we are having this hash map or dictionary, right? So that is order of one operation at each step. So overall it will be order of n, but order of n log n will dominate this complexity. So first we need one left and right value. Left is 0. For right we can take 10 power 5 plus 1, right? Because that is the largest value for any for n. So this is my max. So this is my right value. Now we need one sorted list. I'm just calling it nodes. That will be sorted list. And sorted list is basically from the sorted container. So from sorted containers, import sorted list. This sorted list I'll be initializing with one list that is having left and right initially. Now we need one depth dictionary. So we'll initialize it with 0 with depth 0 and right with depth 0. Now what we'll do, we'll just go over this ordered nodes for value in order. First we have to check where we'll be inserting in this sorted list. We need that index. So the index will be nodes dot bisect left this value. That is basically we are just doing a binary search on this sorted list with this value at which index we have to insert this. So let's say we have 2 and 4 in our nodes this sorted list, and I want to insert 3. 3 will come here. So this I index will be 1. This will return 1. So this will be at 1. So what will be its left and right? Because we want to know the left and the right value of this current node. One of this will be the parent. So that parent of 3 will be at 0 or 1 index, right? So if this is returning index I, so its parents will be either nodes of I minus 1 or at nodes of I. Now how do we decide which one is the parent? We have to check the depth. So we'll be updating this depth dictionary at each time, right? So we'll check the depth of this both. Depth of nodes I, and we need to take the maximum of this one. We don't actually need to know which one is the parent, right? We need to know what is the depth of its parent. So the depth of its parent will be this maximum of this two, nodes of I1 and nodes of I. So what will be the depth of this current value? That will be 1 plus this parent's depth. Next we want to add it in our sorted list, right? So let's just do nodes dot add value. So it will automatically insert this value at the ith index. We just needed this index to get the value, to get the parent's depth, so that we can update the depth of this current value. So after all this, our depth dictionary will have the depth of each nodes, and at the end we can just return the maximum value of maximum depth, right? So max of depth of values. Okay, just run this. It works. Sufficient. And as we discussed, the complexity is order of n log n.